Okay, we are going to continue chapter number 4. Chapter number 5, network layer, the control plane. Okay, so we are in the last class. We have discussed uh, some topics from the chapter number 4. That was the SDN data plane, and then we also discussed chapter number 5, the control plane, and we studied link state routing protocol. Okay, so today we are going to continue chapter number 5. We will continue link state routing protocol, uh, one of its limitation, and then we will try to study the new routing protocol, that is the distance vector routing. Okay, so if in the previous class, if you do remember that we were we discussed the link state routing protocol. In the link state routing protocol, it has basically uh, uh, five steps. Okay, and one of this step was to compute the routing protocol. That was the Dijkstra algorithm was used to compute the shortest routing protocol. Okay, so I would like to just remind to you that how the routing protocol works. Okay, so the first step in the link state routing protocol was that each node has to compute its link state information. Then each node has to broadcast or flood its link state information to all the nodes in the network. When a node receives the link state information from all the nodes, then the node combines the information of link state received from all nodes and construct a graph. That is, a node construct graph from the link state of all nodes. So each node have this complete graph. After this, step number fourth, the each node uh, computes shortest path from itself to all the nodes by using the Dijkstra algorithm. And after computing the shortest path, then each node has to compute the forwarding table. So these were the 5 steps. Okay, now we are going to discuss one of the limitation of the link state routing protocol. The link state routing protocol, it has a problem, and the problem is called oscillation problem. So what is oscillation means? Suppose we have 4 routers A, B, C, D. Okay, these are the 4 routers, and they are connected like this way. Okay, suppose with the B router we have a host. Okay, and that host is sending 1 byte data. How much? 1 byte data. Suppose we have another host here with C router, and this host is sending E byte of data per second, suppose. And this is the D router. So there is also another host, third host, and this host is also sending 1 byte of data. Suppose these 3 hosts, they have sent first packet. They have sent the first packet, and for that first packet, the D router, it used this one path, and the C router, it used this one path, and the B one, it used this path. So you can see that the data on this link is E byte, and on this link, this E byte and this 1 byte it combines. So on this link the data is 1 point, the load is 1 plus e byte, and on this link the load is 1 byte. Okay, suppose these three hosts they send the data, the first packet, and now when the first packet is sent they receive the link state information. That is the C node, it receives the link state information that on this link the load is e byte, on this link the load is 1 plus e byte, on this link the load is 0, on this link the load is 1. Similarly, the D router, it also receives the link state information of the whole network. That is, on this link the load is 1 byte, this link 0, e, 1 plus e. Similarly, B also receive the link state information of whole network. Suppose these three routers B, C, D, these router, they compute or they select the path which is on which there is least load, there is lowest load. Okay, so if these three routers they compute the path, they select the path that has the least load. Okay, so after sending the first byte, and then these node they get this total link state information, the whole network information, each node. For example, B, C, D, they get. Now if B node wants to send the next packet, the second packet, so the B node has come to know that on this link the load is 1 plus e, and on using this link the load is less because here is e, here is 0, here is 1. So this link, this path is less congested, so B will decide to use this path for the second packet. Similarly, C comes to know that this path is, it has more load, and this path it is has just 1 byte of data on this link, so it will also use, or it will also decide to use this path for the second packet. The D node, it will decide that I have sent the first packet on this, and now if the D node want to send the second packet and it has the whole network information, the link state information, then D also knows that, comes to know that this selected path is best one because here the load is 1 byte, and here on this link the load is 1 plus e. So this link, this path, it is more congested, and this path is less congested, so this selected path is better. So the D will use this path again for its second packet transmission. Okay, so now these nodes when transmit, like for example I have said that suppose after sending the first packet, this first packet is transmitted, and then each router B, C, D, they get the link state information. Okay, now if the B node want to send the second packet, then it will use this one path. Why? Because this path is 1 plus e, here is, it is more congested, here the traffic load is more as compared to this path, so it will use this path. Similarly, C will use this path toward A. All these three hosts, they are sending data to A. All these hosts, they are sending data to A. Suppose the destination for all these three hosts is A. So the so C will also use this path. Similarly, D, it will also use this one path for the second packet, this path. Okay, so you can see that the B, C, D, the whole data is moving from here. The B is sending to C and this path, and C is also sending on this path, and D is also sending on this path. Okay, so you can see that here. So what will be the load? So you can see that B is sending 1 byte, so here on this link is 1 byte. Now C is also sending here, so 1 byte of B and e byte of C, so it combines 1 plus e, and here 1 plus e byte of B and C, and D byte, the 1 byte of D, it combines here. So 2 plus E byte load is on this link. Okay, so you can see it. Now this second byte is sent. So you can see that now for the second packet, the B, C, D, they use this path. Okay, now you can see that this path is congested. This path is congested. This path is available free. Okay, so now suppose that this second, the B, C, D, they sent the second packet and they used this path. They selected this path. Okay, now after sending this second packet, each node B, C, D, they come to know about the link state information. So B knows that this path is more congested. So if the B wants to send the third packet, so it will select this path because this has the load 0. Similarly, C will comes to know that this path is less congested as compared to this one. So it will also use this path. Similarly, D will select that this path is 2 plus E. So this path is better. It has low load. So it will also select this path. So all these three nodes B, C, D, they will use this path for their third packet. For the first packet, they used BC used this path and D used this path. For the second packet, the BCD used this path. Okay, so for the third packet, they will use what? The B, it will use this path. Why? Because this path has less load, it is free. Similarly, the C will use this path. Why? For the third packet. Why? Because this path is less congested as compared to this path. Here is the load 2 plus E. Similarly, D will use this path, although this is longer, but it has low load as compared to this one. Okay, so therefore for the third packet, they all B, C, D, they will use this path. So you can see that now the whole load is shifted. All the three nodes, they have shifted the load to this path. Okay, so this problem is called oscillation. This problem is called oscillation. You can note here that this path is, this link is free and the whole BCD, they shift their whole load, their total load on the single path in the second packet. Similarly, for the third packet also, this link is free and this link is used. Why? BCD, they have shifted their total load, their all load on the same link. And why this problem happens? What is the reason? The reason is that when B decide that this path is more congested and this path is free, so it use this one. So B doesn't know that C has also selected this path. The B doesn't know that D has also selected this path, because in the per router architecture, each router have its own control plane. B, C, D, they have their own control plane. Okay, they only interact with these route control that what is their link state information, but it doesn't know that this node B doesn't know that the C and D, they have also selected this path. Similarly, C doesn't know that B and D have also selected this path. Okay, so the control plane, the routing algorithm in the per router architecture is present in each and every router. So each and every router B, C, D, they take the decision by themselves. So they don't know about the decision of other routers. This is why the problem occurs. This oscillation problem occurs. Okay, why this problem has occurred? Again, I would like to emphasize that each router, they have their routing algorithm. They have their own control plane. In per router architecture, I would like to explain to you again. In per router architecture, each router, it has control plane. It consult with the rest of control plane that what is their link state information. But when it decide the route, then it decide the route by themselves, by itself. So it decide the route by itself. It decide the route by itself. It decide the route by itself. So that is the reason. So when this router decide a route, so it doesn't know that whether this router has selected that route or not. Okay. So this is the distributed nature. But in SDN, there is a single controller that decide the route for each and every one. Okay. So let me explain it again. Okay. So why the oscillation problem happens? Why the oscillation problem happens? The oscillation problem happens because in the per router architecture, in the traditional networking. Why? Because when this B node decides to use this path for its third packet, so the B node doesn't know that the C and D have also decided this path. Similarly, when the C use this path, so the C doesn't know that the B and D has also decided this path. So this analogy can be like this one. For example, if there is a road congested, there is a traffic on the road. So if if a lane becomes free, then all the people they move toward that lane. So that free lane becomes the occupied, congested, and the rest of the road it becomes free. So this problem oscillation happens. What is the disadvantage of this oscillation problem? That you can note that all the nodes B, C, D they use the shortest path, the path that has the least load. But and this link is available free. This link is available free. Okay, so it was better to use like this one. If some traffic is moved on this one, some traffic is moved on this path. So it was better. But here you can see that this link is free, and all the three nodes they are using the same path. So this path become congested. So it will increase the end-to-end delay. Okay. So this oscillation problem happens in the link state routing protocol. And why it happens? Because each node decide to select a path independently from others. This B node gets the link state information of A, C, and D, but it doesn't know that the C has also selected this path. The D has also selected this path. So this oscillation problem happens. Okay. So so you know that for the third packet they have also used all BCD they use this same path, and now this link is available free. Okay, but this all the traffic is moving on the single path, and this path will become congested. Okay, and this will increase the end-to-end delay. Okay, so this problem happens. Why? Because due to traditional networking distributed nature, that each router decides the path by itself. It doesn't know that other router what they have decided, because in the traditional networking or in the per router architecture, each router have its own control, each router have its own routing algorithm. Okay, so similarly, if these nodes they want to send their fourth packet, then for the fourth packet they will use this path. Why? Because this path is free, so D will select for the fourth packet this path, and C will also select this path, then B will also select this path. So you can know for the fourth packet this will come. So this will happen for the subsequent packet. The fifth packet will be again sent on this path. Okay, so you can see that what is the problem in oscillation? The problem in oscillation is that this link is free available, and the whole traffic is moved on the single path, and their single path becomes the congested. Okay, so this oscillation problem happens in the link state routing protocol. And why it happens? Because of in distributed architecture. Why? Because each router it decides the path independent from the decision of other routers. The B doesn't know that the C and D have also decided to use this path for their third packet. Okay, so this problem can be removed by SDN easily. Why? Because in SDN we have a centralized controller. The centralized controller, it computes the path for B, C and D. It decides the path for B and C and D. Okay, so if there is a centralized control that decide the path for B, so if for B if it selects this path, then for C it will see that, oh, if the traffic is moved, if for C and D the traffic is also moved on this path, then it will create congestion. So this problem will not happen in centralized controller. Why? Because in centralized controller the control plane is on the single machine, and that centralized controller, it computes the path for B, C and D. So it will know that if so in this centralized controller this oscillation problem will not happen, because in the centralized controller the controller computes the path or decide the path for B and C and D. So if it decides the path for B, this one, for C, this one, so if it decide to move the traffic on this one, so it know that already the D traffic is moving on this link. Okay, for D this path is selected. So if the C traffic is moved on this path, so it will not create any difference, because here the traffic is also 1 plus N, and here the traffic will also become 1 plus E. Okay, so it will not send the packet, so the second packet on this path. Why? Because this path is optimum. Okay, similarly, so this centralized controller, it removes this path, this oscillation problem. Why? Because in the centralized controller it computes or it decides the path for each router for B, C, D. Okay, so and the oscillation problem happens in the per router architecture. Why? Because each node decides its path by itself, so it doesn't know that what a path has decided by other router C and D. So this is due to distributed nature. Okay, so now we are in the next video we would like to discuss the distance vector routing protocol. Okay.